Hi everyone, today we'll do Cambridge A-Level Further Mathematics, Syllabus Code 9231, and this is Further Pure Paper 2, Variant 3 from the May June 2025 series. We go for question 3 today. I've already done question 1 and 2 previously. Okay, question 3, they're giving you this equation. There's two variables here, y and x. So we are also given at the point 4 1 over 3 on C, the gradient or dy dx is a negative 1 over 2. So we know from this information y is a function of x. And so we want to find or show that dy dx is this value. So uh, given that this is like slightly not a straightforward equation or not an explicit equation in terms of x and y, we'll have to use what we call the implicit differentiation on this one. So we take the entire equation and we take the derivative in terms of x, right? So 9y squared, okay, first how you're going to differentiate is first you differentiate with respect to y. So the derivation behind it is like, we want to differentiate, I'll just look at the 9y first, 9y squared. We want to take the derivative in terms of x, right? But it's a function of y. I mean the function y in terms of x. So it's actually a composite function, for which you need to use the chain rule. So actually what we're doing is we take the derivative in terms of y first, like that, and then we multiply by the chain rule dy dx, so that the differential of y and differential of y cancels, and we're left with the what we call differential in terms of x. So what we do is differential in terms of y, you get 18y and the power minus 1, so you just power 1. And don't forget, you need to multiply by dy dx here. Okay, so that's the basis behind what we're doing here. So we need to treat y as a composite function in terms of x. So maybe I'll just highlight this in red, so that just as an example for the 9y squared. So the rest of it I'm gonna do quite straightforward. So 9y squared we've already proven, or sorry, we just leave it there first, and then maybe for the 3 hyperbolic inverse sine, I'll use blue to highlight it. And okay, so we want to take the derivative in terms of x of a negative 3 inverse hyperbolic sine xy. Okay, first of all, we take the negative 3, we just take it out first. And then we're also gonna differentiate the inverse hyperbolic sine, if you forget about that. So there's a formula sheet, right? So inverse hyperbolic sine, you get this one. So we take the derivative in terms of x first. Again, we just have to do the 1 over 1 plus xy and squared. Okay, so this is taking derivative in terms of the inverse hyperbolic sine. And then the chain rule, we need to multiply by the derivative of the inside function, which is xy. And xy, we need to treat it as a product because y is a function of x. So um how we're going to do this is we take the derivative of x, then we leave y, so that derivative of x is just 1, so we just leave it. And now we take the derivative of y and multiply by x. Okay, we leave the x, take the derivative of y, that is just dy dx, right? So we're left with this one for this derivative. And on the right hand side, the entire right hand side actually goes to 0, because it's just a constant here. 1 minus 3 natural log of 3, that's just a constant. So the entire right hand side goes to 0. And let me simplify this a bit more. Okay, so we're left with this, and therefore we're gonna write it back into the equation, or maybe I use the blue to highlight. Okay, this is just the blue part again. So I have substitute everything back into the equation. 18y dy dx minus 3y plus x dy dx divided by the square root of 1 plus x squared y squared equals to 0. Okay, on the right hand side, everything equals to 0. And we want to show at this point, we want to find dy dx. So, okay, we don't really have to simplify anything first, because all of this eventually will reduce down to some numbers. So we're just going to substitute the numbers straight away in first. So at 4, 1 over 3. Okay, at the end, you should be able to prove, I mean, after substituting all the values, it's just a matter of doing your computation, you just typing your calculator or whatever simplification about numbers lah. So this one is relying on your calculator or whatever mental calculation you have, but you should be able to show that this is true. Okay, it's all just a matter of substituting numbers in. Okay, so this is for part A. And part B, they want you to find the second derivative. Alright, so let me just copy down we copy down this equation first. Okay, what we do here is again we take the entire derivative in terms of x on both sides, and we're gonna deal with the individual case. So this is gonna be slightly longer. Okay, first the first term, the derivative of 18y dy dx in terms of x. And we treat this as a product. Okay, 18y, I mean y multiplied dy dx, there are two functions. So 18, I mean the 18 is just a multiple, so I'll just take it out. Y differentiated, you become dy dx, and then I'll leave the dy dx, so that just becomes there. And y, I mean I'll add y, I'll leave the y, and I'll differentiate dy dx to get the second derivative. You see, this is using the product rule again. So altogether we get 18 dy dx squared. This is not the second derivative. This one is the square of the first derivative. And now we have y multiplied the second derivative. Okay, so this is the first term taken the derivative. Now we take the second term. Okay, this is the red part. Okay, the second term is going to be slightly more longer. Okay, we take the derivative in terms of x of. Okay, so first of all, the negative 3 again, I'll leave it out. It's a multiple. And then we have this function is a quotient. So quotient, firstly, we leave the bottom function, we bring it up. Okay, we bring it up and we just write it. So we have 1 plus x squared y squared. And we take the derivative of the top function, which you get dy dx. Then we take the derivative of this one. Okay, x dy dx. This is a product again. We need to use the product rule. So I differentiate x becomes just 1, and I get dy dx. I mean, I'll leave the dy dx, and we add we leave the x dy dx multiplied. I mean, dy dx, you take the derivative again. That's the second derivative. So d square y dx squared. Okay, so that is the first part of the product rule. Then we have to minus. Okay, this is the quotient rule. Okay, quotient rule minus. Leave the top function and take the derivative of the bottom function. Okay, bottom function, there's a square root which is power half. So I take the half in front, and the square root goes to the bottom. 1 plus x squared y squared. And we need to use the chain rule, take the derivative of the inside function, which is 1 plus x squared y squared. So we need to use the product rule again. X squared y squared is a product. So we multiply up here. I'm just going to straight away multiply up here because it's a 1. So you get, okay, I differentiate the x first, which is you get 2x, and we leave the y squared. Then differentiate the y, which you get 2x squared y, and remember to use the chain rule, dy dx, up here also. Okay, so, and entire thing divided by the bottom, 1 plus x squared y squared squared. So the square and the square root cancels out. Let me rewrite this so it's not so messy. Okay, and it's quite a long or quite a large equation or expression, but yeah, let's combine the two and substitute the values in. Okay, so I mean I've combined the two derivatives now, and now we substitute, okay, the value. Uh, we substitute the value of 4 1 over 3, and then also dy dx evaluated that x equals to 4 is negative half. Okay, we've proven this. Sorry, x equals to 4 and y equals to 1 over 3, right? This is the specification. So dy dx is negative half. So, okay, now again, it's a substitution of the values. As long as you're careful with the substitution, you should be okay with this. So I'm gonna substitute the values now. Okay, so after all the working, you should be able to get the second derivative of this equation to be 29 over 4. So yeah, the hard part probably will be doing the second derivative part where you need to differentiate this quotient. I mean, you use the quotient rule, product rule, chain rule all together, right? So as long as you differentiate this carefully, you should be fine. And also the substitution of the values carefully. So barring any careless mistakes, so this will be good lah. So but if you're wondering any real life application of this, probably you have to, if you're going into applied maths, although all those physics. But yeah, this is I mean, implicit differentiation is a good practice to have, and to a good skill to know as if you're going into any of the fields where maybe physics, maths, or even engineering, any branch of engineering. So yeah, so this is implicit differentiation. That's it. Thanks for watching.